So, I'd like to start the second half of my talk. So in the first half, I introduced you what quantum chemistry simulation can do, and then I talked about the Schrodinger equation and Born-Oppenheimer approximation to show you what kind of equation we want to solve. And afterwards, I was talking about Hartree-Fock methods. Now, I'd like to talk about the other methods, which are semi-empirical methods and perturbation theory, configuration interaction, coupled cluster methods, and density functional theory. So I'd like to start from the semi-empirical methods. Here is the concept of semi-empirical methods. So first, we treat only the valence electrons. So in the basis set part, I mentioned that core and valence are available. In some cases, core are treated with less functions and valence with more functions. Here, they are a bit more aggressive. We remove the effect of the core electrons. And we also use the minimal basis sets to reduce the number of, reduce the computational costs as much as possible. And also we introduce another approximation, the zero differential overlap approximation. What we're doing is we're going to approximate the intervals, or we're going to reduce the number of integrals to be evaluated. So first, let us focus on this one electron integral. So it has the electron nucleus attraction term. So we have a nucleus here, and it's the center of atom A. And this has a function at center B, atom B. And this function has a center at atom C. In this case, if all A, B, and C, if they're all different, it will be 0, and this integral will not be evaluated. So only like AAB or ABB or AAA, those kind of integrals will be evaluated. So by doing so, we could reduce the number of terms to be evaluated. We did a similar thing for the two electron integrals. Again, mu has the center at atom A, and nu has a center at atom B, and lambda has a center at atom C, and sigma at D. So in this case, if A is not B or C equals not D, they'll be 0. So only the terms with A equal B and C equal D survives. So now you see we could reduce a large number of integrals to be evaluated. So you see the concept. Rather than the accuracy, we want to solve the problem with low computational cost as much as possible. So here are here's the list of the famous semi-empirical methods. The first three are using the zero differential overlap, which I just explained. So the neglect of diatomic differential overlap, the NDDO method, uses the zero differential overlap approximation what I just showed you. The intermediate neglect of differential overlap, INDO method, reduces the number of integrals even more aggressively. So what they do is they only evaluate these integrals. So originally it was like mu, nu, lambda, sigma, but they only accept the same type of orbitals here. So these are exactly the same, and these are exactly the same. And these are all on the same center of one nucleus. And complete neglect of differential overlap is even more aggressive. So they only use these integrals, and the other integrals are not evaluated. They're 0. And there's other families of semi-empirical methods, and they can be classified based on the parameterization. By the way, these have parameters, but in this case, these three are parameterized so that they'll match the ab initio molecular orbital method results. In this case, they're parameterized so that they'll match with experimental results. So the parameterization has a bit of a different concept here. And for modified NDO, MINDO, the parameterization is done based on bonding atoms. So it's a diatomic parameter. For instance, if we have CNH, it'll be a parameter CH. And modified NDDO, MNDO, has atomic parameterization. So they have a parameter of atoms carbon or like carbon of hydrogen. And they can definitely tackle larger molecules compared to ab initio methods. However, there are some drawbacks. So this lack of some parameters for new molecular systems. So someone needs to make a suitable parameter for a given system. But if it's completely new and there's no parameters for it, you can't compute it. And on the other hand, if it's ab initio, if it's consisting of existing atom, we don't need any further parameters so we could tackle any kind of new molecule we want. And also the performance in the sense of accuracy is less reliable compared to ab initio methods. But at the same time, they're improving. So there's PM7, which has dispersion correction, so they can treat the weak interaction quite well. So these are the semi-empirical methods. So now I'd like to move on to talk about the correlation methods. So first, I'd like to show you how good did Hartree-Fock do. The Hartree-Fock method actually calculates the 99% of the total energy. So it's not actually doing that of a bad job. However, there are many cases where Hartree-Fock methods do not provide enough accuracy. So we want to improve the Hartree-Fock results. So if we know, for instance, know the exact energy, and this is our Hartree-Fock energy, the gap between them is called the correlation energy. Because at Hartree-Fock, we don't explicitly treat the interaction between the electrons. We use the mean field approximation. So what we want to do is that we want to calculate this correlation energy efficiently. So, and those are the methods shown below. They're called the electron correlation methods. The configuration interaction, couple cluster method, and the perturbation theory. And I'm going to talk about these one by one. But before that, I want to talk about the second quantization, which is convenient to discuss the electron correlation methods. So we have spin orbitals of chi-p, which are molecular orbitals. And in second quantization, what we want to do is we want to quantize the field. Well, the field where the electron is using the spin orbitals, rather than describing the spatial distribution. So for each determinant, which is the Fock state, is represented by an occupation number vector. So what I mean by that, so assume here that K is a Fock state, and we have elements of K1, K2, and Km. So if the orbital is occupied in this orbital, we have a Kp is unoccupied, Kp will have a value of 0. And if it's occupied, if there's an electron there, Kp will have a value of 1. That's what I mean by the occupation number vector. And we could introduce two new important and convenient operators. So that's the creation operator, P. So here's this later determinant, and if we act the creation operator, we can make a new spin orbital here. And the annihilation operator, we could do the other way around. If we have AP here, it removes or destroys this spin orbital. like this. So now what that means is that if we have a Slater determinant of vacuum, which is 0, by using many creation operators, we could make a Slater determinant of n electron starting from the vacuum. So we could sort of introduce electrons in the Slater determinant using the creation operator. And using the creation operator, the annihilation operator, we could determine the second quantized Hamiltonian as this form. HPQ is the one body term of the Hamiltonian. It's one electron integrals. So it has the kinetic energy term of the electrons and the electron nuclear attraction term. And for this two-body term, you have this two electron integrals, which is the contribution for the electron repulsion. And if you see this integral, do you see any difference from the integrals here and the integrals I wrote previously in the different slides? Well, if you see the others carefully, what I used to write was xp star x1 times xq x1, chi p star x1, chi q x1, chi r star x2, chi s x2. I think that I would be writing in that kind of form. That form is called the chemist notation. And this notation is called the physicist notation. I wrote this integrals in the physicist notation on purpose because in Qiskit, it is in this order. So if you're using both quantum chemistry simulation codes and Qiskit, please be aware that the ordering can be different. And next, I'd like to briefly explain how we construct the Hamiltonian. So what I mean by construct is we're actually calculating and transforming the one body into one electron integrals and two electron integrals from AO form to MO form. Here, AO are labeled by the Greek letters, and MO, molecular orbitals, are labeled with PQRS. So how do we do it? We do a matrix-matrix multiplication using the coefficient matrix, the molecular orbital coefficient matrix C, which is optimized by the Hartree-Fock method. So here you see that the AO labels here and MO labels here. So they'll be transformed into this using matrix-matrix multiplication. And for two electron integrals, we perform this one by one. So using the C again. So sigma will be transformed to S, lambda to R, nu to Q, and mu to P. So what we're actually doing is transforming the atomic orbital Hamiltonian into a molecular orbital Hamiltonian. So that's how it's done. And it's actually done this way in Qiskit as well. So now I'd like to move on to talk about configuration interaction method. It's called the CI method. So in Hartree-Fock, we describe the wave function with a single Slater determinant. In configuration interaction, we describe the wave function here as a linear combination of Slater determinants, like this. So let's look into this. So here, this is the Hartree-Fock determinant. And what's this? What it's actually doing is starting from the Hartree-Fock determinant, it destroys a spin orbital and it creates a spin orbital. In other words, we could say it's removing one electron and it's adding one electron. So if you see here, starting from Hartree-Fock Slater determinant, you remove one electron and you add one electron. So this corresponds to a single excitation Slater determinant. And next, if we see this, we have AB, AB, AAAB, AJAI. And first we have two annihilation operators, so we destroy or remove two electrons from the Hartree-Fock determinant, and we add two electrons in the Slater determinant. So this corresponds to double excitation Slater determinant. And here again, we have three annihilation operators and three creation operators. So we remove three electrons from the Hartree-Fock determinant, and we add three electrons in determinant. So here it corresponds to the triple excitation determinants. So that's what I mean by the linear combination of Slater determinants. So we're describing the wave function of this configuration interaction with a linear combination of Slater determinants. And in configuration interaction, we determine this coefficient C. If we don't truncate at any excitation, so what that means is if it's an n electron system, we consider up to n electron excitation. That is called full CI, the exact diagonalization in physics. So in that case, it'll be exact in that given basis. So now I like to consider how to solve this CI. So here is the CI wave function. We put it in the Schrodinger equation, and using the variational theorem, we want to minimize the expectation value of the Hamiltonian under the constraint of the wave function, the overlap of the wave function being normalized. So we're minimizing this under the constraint of this being 1. So we use the variational theorem, and we end up with this equation. So we're going to solve the eigenvalue problem in CI. However, note that the number of elements in this matrix scale exponentially against the system size without truncation. And even if we truncate, the number of elements are quite large. So we do not explicitly diagonalize the full matrix. We use a method called Davidson method, which we diagonalize the subspace, the reduced subspace iteratively, and we only get the low-lying roots there. So again, we do not explicitly diagonalize the full matrix, but here we use a smart way to diagonalize the subspace to make it a small problem. Now I'd like to move on to show you how the CI matrix, this matrix looks like. So here we have the Hartree-Fock Slater determinant, single excitation determinant, the double excitation determinant, triple and quadruple. And I also have the Hartree-Fock determinant and single, double, triple, and quadruple excitation determinants here. So you see that most of these have values, but there are some zeros in the elements. So why is this 0? So the Hartree-Fock and the Slater determinants don't have the value. Why is that? It is because this term is corresponding to the off-diagonal elements in the Fock matrix. In Hartree-Fock, what we do is we diagonalize Fock matrix. So only the diagonal elements should survive. The off-diagonal elements should all be 0. So that is the reason why these are all 0. By the way, this is called the Brillouin theorem. And we can also find 0 in other reasons as well. They are based on the Slater-Condor rules. So since our Hamiltonian has only one body and two body terms, these have only values up to the difference of 2 electron excitation because we only have 2 body terms in our Hamiltonian. So if there's 3 electron excitation difference, then it won't have a value. That's what Slater-Conway rules are. So if you see Hartree-Fock, up to D, we have a value. But T, it's a 3 electron excitation difference, so we don't have a value. And of course for Q as well. And for the singles, we see up to T, we have the value. For Q, it's triple excitation difference, so we know these value will be 0. So if we consider Slater-Condon rules, this matrix will be a band matrix. It's sparse, more sparse than maybe you assumed, but still the number of elements will explode if you create a system size. So usually you truncate your excitation at a certain point. So practically, we use a truncated configuration interaction, and CISD, this configuration interaction, which considers single excitation and double excitation determinants, are practical. So, but we'd like to see what happens if we use this truncated CISD. Let us assume that we have a system of 2 particles which are very far from each other. So if it's extremely long, then if they don't feel each other, the energy of this system should be the summation of the energy of A and energy of B. And for the exact diagonalization full CI, this will hold. How about when we truncate this? So if we have a Hartree-Fock-Slater determinant for A and a Hartree-Fock-Slater determinant for B, then it should be a Hartree-Fock-Slater determinant for A and B. And if we have a Hartree-Fock-Slater determinant for A and a doubly excitation determinant for B, then we should have a doubly excitation determinant for a system A plus B. And if we have a doubly excitation determinant for A and a Hartree-Fock determinant for B, then we should also have a doubly excitation determinant for A plus B. So this is okay, but however, in this case, if we have a single excitation determinant for A and double excitation determinant for B, then we should have a triple excitation determinant for A plus B. And if we have double excitation determinant for A and single excitation determinant for B, then we should have a triple excitation determinant for A plus B. And if both of them are double, then for the full system, we should have a quadruple. However, I just mentioned that we're truncating at D, so if we use CISD, these terms cannot be considered. So what happens is that the A plus B will not be A plus B. This is actually critical because what we do in chemistry is that we form and break bonds. So what this is saying is that we can't describe that accurately. So CISD is not size consistent, it's size inconsistent. So it's not consistent with this rule. So this is the reason why CISD is not used that much practically, and rather a couple cluster method, which I'm going to show you in the next slide, is widely used practically. So here is the couple cluster method. The couple cluster ansatz is as follows, and here the cluster operator shown here is an exponent. And the cluster operator is like this. So if we see T1, it's the coefficient TIA and the creation and annihilation operators. So this was the same as what we saw in CI. well, we can make it more general with the parameter of single excitation and the general single excitation operator. And we could also, if we see T2 as well, again, Tijab will be the coefficient, and we have two creation and two annihilation operators. So this part seems very close to CI. And however, these will be in the exponent. So what will happen if it's in the exponent? So we can expand it in Taylor series. So if we expand it, we have 1 plus T1 plus T2 plus up to Tn plus, so we have the second order, and so on. So we have these terms. So the I plus T1 plus T2, the first terms, T1 plus T2, is exactly the same as what we saw in convolution interaction. They're called the connected excitations. But not just that, in coupled cluster method, we have these higher order terms, which are called the disconnected excitation terms. And by the way, so now in coupled cluster, unlike CI, we have the higher order terms in our wave function. And because of this, coupled cluster methods are size consistent. Even though if we truncate it as CCSD, they'll still remain size consistent because we have this higher order excitations. So now we have the coupled cluster wave function, and we'll put it in the Schrodinger equation. And it will be like this. So you have the exponent and Hartree-Fock determinant. And if we multiply exponent minus t from the left-hand side and project it to all the Slater determinants, we get these equations. Only this term, the projection to the Hartree-Fock Slater determinant, has a value. And this term will be the energy expression of coupled cluster. And the other equations, if we assume that the orbitals are orthogonal, then these equations, which are called the amplitude equations, they'll all be zero. So what we're going to do is that we're going to solve the coupled cluster amplitude equation until this zero condition will be fulfilled. And we can do that by optimizing the parameters of the cluster operators. And once it's optimized, then we can compute the energy of coupled cluster using that optimized coefficients or parameters. So this equation is the nonlinear equation, and we can solve it and get the energy, coupled cluster energy. And as I mentioned, it's a size consistent, so because of the higher excitation terms of the disconnected terms. And the coupled cluster is not variational, by the way, but it is frequently used because it's extremely accurate. And so the typically used coupled cluster is CCSD. So CCSD considers up to single and double excitations. And if we consider CCSD-T, then it'll be extremely accurate. We'll consider up to triple excitation. However, CCSD-T is a bit too expensive. So what we do instead is that we treat the triples perturbatively. That method is called CCSD parenthesis T. This is known as the gold standard method in quantum chemistry. So practically, this will be the value computed using this will be close to the answer. Okay, now I'd like to move on to the unitary coupled cluster. So here is the ansatz of unitary coupled cluster. What's different from the conventional cluster ansatz is that in addition to T, we have this minus T dagger. This T dagger is called de-excitation operator. But the remaining cluster operators are exactly the same as the coupled cluster ansatz, the conventional coupled cluster. But since this exponent t minus t dagger is unitary, a unitary coupled cluster is variational. So why don't we use this? But however, if we want to implement this on the classical computer, the conventional CCSD, so this is the expression we saw in the energy expression and the amplitude equation. So, and if we see this, this actually terminates a finite order. However, in unitary coupled cluster, this term, there's no termination point, so we have to truncate at a finite order. So what that means is that if we want to implement this on a classical computer, we'll be actually losing the advantage of unitary coupled cluster. By the way, unitary coupled cluster it's used as ansatz in Qiskit's VQE. And so in case of the quantum algorithm, UCCSD doesn't have to be truncated, and it could be implemented easily on a quantum algorithm. And also, coupled cluster, the conventional coupled cluster, and if you want to implement on a classical computer, it takes an enormous effort to create and develop the code and run it. However, in the case of unitary coupled cluster for the quantum algorithm, it's relatively easy to implement. So in that sense, we're seeing some kind of advantage using quantum computers. So now I'd like to move on to the perturbation theory. Sorry. Excuse me. Okay, I'm going to start with a general part, which is I'm going to talk about the Rayleigh-Schrödinger perturbation theory. So what we want to do is we want to map an inexact operator to an exact operator using perturbation theory with increasing order of accuracy. So we start by partitioning the Hamiltonian. And this zeroth order Hamiltonian, we know the solution of this. And if we assume that the perturbation is small, the perturbed energy En and the perturbed wave function psi n can be expressed as power series like this. And if we introduce this Hamiltonian and this energy expression and wave function in the Schrödinger equation, then it'll be like this. And comparing coefficients of each power of lambda, then what happens is that we could arrive at the general kth order Schrödinger equation like this. And if we have the zeroth order Hamiltonian on the left, then we could get the general kth order energy correction, which is like this here. So this is the zeroth order wave function, and this is the H1, the first order Hamiltonian part. So, and this is the wave function of one order less than the order of the energy. So that's what you need to calculate the kth order energy correction. And how is the kth order wave function calculated? It's calculated, it can be the perturbed wave function here. It's actually a linear combination basis of unperturbed wave function. So it's a linear combination of the zeroth order wave function. And by the way, if you calculate, you can get the first order perturbed wave function, which is like this. So now I'd like to move on to the practical calculation. The Møller-Plesset perturbation theory is the widely used perturbation theory. So what we do here is we partition the Hamiltonian in a way that the zeroth order Hamiltonian is a sum of Fock operators. So we want to map this Fock operator to the correct Hamiltonian. So the difference between the correct Hamiltonian and the Fock operator is shown here. It's called the fluctuation potential. It's the difference between the real, 1 over Rij, 2 electron term, and the mean field approximation. So this is the mean field approximation in the Fock matrix shown here, the Fock operator shown here. So what we want to do is map this Fock operators to the correct Hamiltonian using this fluctuation potential. Okay, so we already solved the zeroth order Schrodinger equation. And so the wave function we get is the Hartree-Fock wave function. And the zeroth order energy is using the Hartree-Fock wave function and the zeroth order Hamiltonian, which is the Fock operator. And what we get is this. We don't get the Hartree-Fock energy. Remember, if we diagonalize the Fock matrix, what we get is the Hartree-Fock wave function. This wave function is eigenvectors, and we get the orbital energies as the eigenvalues. So the first order energy is actually the sum of those orbital energies, those eigenvalues. Now we consider the first order energy correction. So first order energy correction is like this. So H1 is here. But if you remember, both 1 over Rij and J and K, they're both the terms of the 2 electron integrals. So they actually end up like this. So this is the Coulomb term, and this is the exchange term. And what this is actually the difference between the Hartree-Fock energy and orbital energies. So what this means is that the zeroth order energy and the first order correction add up to Hartree-Fock. So the first order correction to the energy is just regaining the Hartree-Fock energy. Next, I'd like to move on to the second order perturbation. The first order wave function is shown like this. And the second order energy correction is like this. So here, the wave function, we consider the first order wave function for the second order correction, energy correction, and we use this H1, the fluctuation potential. So if we insert this into here, we get this form. So this is still the general form, but what actually is this? So this denominator is the energy difference as zeroth order. So what that is, it's a difference in orbital energies. And what this is, it's a zeroth order wave function except n. And in this case, it's Hartree-Fock. So besides Hartree-Fock, is what we're saying is that we're going to consider all Slater determinants besides Hartree-Fock determinant here. So here we should consider all Slater determinants. However, the singles do not survive because of Brillouin's theorem, and the Slater determinants over triple excitation does not contribute, again, because of Slater-Condon rule. So only the doubles survive. So we only have to consider the double of the Slater terms of double excitation, like this. So we're going to compute the 2 electron integrals and orbital energy difference of the 2 electron Slater determinants. So it'll be in this form. And the convenient thing of MP2, the second order perturbation, is that it does not require an SPF procedure. So it's sort of a one-shot calculation. So it's quite convenient and it's costs less compared to coupled cluster. However, if we think that maybe MP2 is good, then why don't we have MP3, 4, 5? It should be better. However, that's always not the case. Sometimes the error, the result oscillates and it doesn't converge. So in some cases, increasing the order of perturbation does not always result to better results. So that's the reason why most of the people use MP2 up to the second order. So last of all, for the correlation method, I just want to touch about active space, CI, and CC. The reason why I want to touch this is because the active space transformer is in Qiskit, and I think you may have an experience to consider using the active space. That's the reason why I want to explain the concept of active space. So I mentioned in CI about truncating the excitation. But maybe there's another way to truncate. Why don't we just truncate the space of performing the configuration interaction? What that means is that we were considering all electron excitations in all the orbital space, but we were reducing the number of excitations. But rather than reducing the number of excitation, we could just reduce or make the space smaller so that we can treat even the full CI in the space. By the way, in chemistry problems, this unstable orbitals with electrons and stable unoccupied orbitals, these orbitals actually play an important role in most of the chemistry problems. So therefore, it makes sense to treat these important electron orbitals more accurately than others. So that's the concept of active space. And so we could do CI in this space, but not just that, we could even optimize these, re-optimize the orbitals. So we can make the orbitals optimizing the Hartree-Fock even more better. So those methods are called multi-configurational SCF. If you're using the truncated CI, you're using truncated CI in this given space. And if you're doing full CI in this given space, it's called a complete active space self-consistent field method. So you could even optimize the orbitals. So if by doing that, you get a smooth and nice potential energy surface or curve, even though it's a difficult problem such as the multi-bond dissociation problem. It's usually hard to tackle, but CAS-SCF could compute the potential energy surface accurately. However, the energy value itself is not that good. So in many cases, people do either perturbation or CI or CC on top of that. So they're using rather than using Hartree-Fock wave functions as a reference, they're using MCSF or CAS-SCF wave functions as a reference. That's called a multi-reference method. And last of the correlation method, this is the last slide of the correlation method section. So I'd like to mention about the scaling of the correlation methods. So Hartree-Fock gets the 99% of the total energy at the cost of n to the power of 2 or 3, and it is the system size. Then MP2 gains the 80% of the last 1% in the order of n to the power of 4 to 5. And CISD, the truncated CI method, gains 90% of the last 1% with the order of n to the power of 6. And CCSD, the truncated coupled cluster, gets 95% of the last 1% with the same effort. And the CCSD parenthesis D, the gold standard, gets over 99% of the last 1% at this cost. So you see, we can achieve systematic improvement using correlation methods. And seeing that the computation resource for full CI grows exponentially against the system size, you see that the correlation methods are doing a good job by efficiently computing the correlation energy. So I've talked about the correlation methods, the electron correlation, the second quantization, and I talked about the methods of configuration interaction and coupled cluster methods and perturbation theory, and especially the MP2. Now I also talked about the active space. And I also introduced the Brillouin theorem, the Brillouin theorem, the Slater-Condon rules, and size consistency. Now, finally, I'd like to talk about the density functional theory. So first, I'd like to talk about Hohenberg-Kohn theorem. The first theorem is the electron density, described as rho xyz, it's only three-dimensional. It uniquely determines the external potential, which means it determines the charges and position of the nucleus. So the properties of any electron system in the ground state is determined by the electron density. And the second theorem is the electron density minimizes the energy functional of this, which depends on rho. So what that means is we can start from a trial electron density and optimize it to get the minimum using the variational theorem. So if we know the functional, then we can optimize it and get the true electron density. And then if we get the true density, then we can get all the properties of a main electron system. And unlike wave function theories, this is extremely simple, so it's very appealing. However, there is a drawback. We don't know how the energy functional, the true one, or the exact one, looks like. So here is the energy function at that moment. So this is the energy functional, and we have four terms. So let's look into this term. It's the electron nucleus attraction. So Z is the charge of the nucleus, and rho is the density of the electrons. And this is the distance between the nucleus and the electron. So see, this is actually almost exactly the same as what we saw in the Hartree-Fock and the other Hamiltonian terms. So this seems to be obvious or trivial. And the next term, J, is the Coulomb interaction. So here you see you have a Coulomb interaction between two electron densities. So this is also exactly the same as what we did in Hartree-Fock. So these terms are quite obvious. However, at that time, how we describe this kinetic energy, that was not trivial. So the relation between the kinetic energy T and rho was not trivial at this moment. And also the exchange correlation potential. So in DFT, we have the exchange part and the correlation part as a functional. So this part was also not trivial. So then Kohn and Sham introduced a new concept. What they did was they reintroduced the orbitals. And Kohn and Sham proposed to use a fixtures model of non-interacting electrons. It's very similar to Hartree-Fock, and they're assuming that the density in this fixtures model is the same as the one of the interacting electron system. So they're saying that it's exact. So the density corresponds to the wave function described as a Slater term here. So we're actually doing sort of the same thing in Hartree-Fock. And the kinetic energy is also the same as what we do in Hartree-Fock here. So this is quite accurate. So T was actually a mystery, but they provided some kind of not a solution, but they find it a better way to treat the kinetic energy by using the orbitals. So here is the Kohn-Sham expression of the energy. So Ts is the kinetic energy using the spin orbitals, and VEN is the electron nuclear attraction, J is the Coulomb term, and EXC is shown like this. So there's the exchange potential, the correlation potential, and there is this T minus TS. TS, we know what it is, but T is probably the true, is the true kinetic energy. So what this is doing is that this includes some kind of errors. So we're tucking in the error or the modification of error in this exchange correlation potential. So we're putting all the ambiguity in this exchange correlation functional. And by minimizing the energy functional by minimizing the energy functional by varying the orbitals, we arrive at the Kohn-Sham equation shown here. And the effective potential here is described by the electron nucleus attraction term, the Coulomb term, and exchange correlation potential, which is the gradient, the first derivative of exchange correlation functional against density rho. What Kohn-Sham equation allows us to do is that it allows us to perform the SCF calculation for DFT. And what's appealing is that we have the correlation in this exchange correlation potential. So what that means is that we can treat electron correlation with the same or smaller cost compared to Hartree-Fock. But one problem still remains. So we don't know the true exchange correlation potential. We don't know the exact functional. So what we can do is that we can't systematically improve the performance. So we could improve the performance of DFT perturbatively. So, sorry. We could do that one by one. So we start from the local density approximation. So we use the electron density, and then we can refine that using the gradient of density, which is done in generalized gradient approximation. And then we could use the second derivative of the density and the kinetic energy density to modify that. So you see we're climbing up the ladder one by one. And here we could also modify the functionals using the Hartree-Fock exchange. So they are called Hartree-Fock. So they're combining DFT and the wave function methods. And so the most famous one is probably the V-through lip. And the development of V-through lip made chemists excited, and almost everyone started to use DFT after the development of the hybrid GGA. And the number of people using DFT has increased and increased and increased. So nowadays, I think more than 90% of the quantum chemistry articles are based on DFT. So you see, DFT is appealing because you can treat correlation with low cost. But the drawback is that we can't improve the performance systematically. Okay, this will be the end of my talk. So I have talked about what quantum chemistry simulation can do in the introduction, and I talked about what kind of equation we need to solve, and then I talked about the quantum chemistry methods. I talked about all these methods and also talked about the basis sets and atomic orbital integrals. I hope now you're a bit more interested in quantum chemistry, and I hope I didn't make you bored. If you're interested, these two textbooks are the ones I recommend. In Zabel and Oslin's books, I really like the chapter of 1, 2, and 3 in the textbooks. And for the electron correlation methods, I like the Helgaker, Jorgensen, or Nelson's book. Okay, so this will be the end of my talk. Thank you so much for your patience and time. And I hope you enjoyed it, but uh, I'm looking forward to see you soon. But uh, before that, I'll say bye for now. Thank you so much for again, and have a great day.